Dr. Julio Pulido. I'm a vice president of global quality and reliability engineering for Phononic. I have 20 plus years of experience in the area of reliability engineering, testing, validation, qualification. We do analytics. I get into analytics, testing, quality controls, assurance, you name it, right? And also, I'm part of the IEST as the vice president, and the reliability and support team. Ben, in his tenure as the president, and I think we can really take it from here. So, if no other questions, I'm gonna go ahead and start going through. Feel free to stop me anytime, or and then I answer the questions as we go. So the number one, let's start talking about why or what is ESS. We can go to the entire list. It's quite an enchilada. It's 6 points. But the purpose of ESS is about improving product reliability. And why you do it, right? That's the main thing, you know. You want to improve the product reliability. So you will say, okay, reliability has to do with long term. That's correct. But also it affects you depending on how the product is used, what kind of product you are dealing with. Then you need to look at exactly if ESS is necessary for you or not. So those are the things, right? But it involves planning, environmental testing or applications, failure analysis, and with that goes physics of failure. So then once after that, you can do a verification testing, documentation, and traceability as part of quality assurance. And also other main reasons, right? What should we use it? Why, right? So now that we know ESS, why? When you should use it, when is really necessary. If you have high reliability applications for the get-go, or your industry requires a high level of performance in terms of low failure rate, this is your answer. If you are not able to eliminate all the failure mechanisms, or some failure mechanisms, you cannot control it well in your process, that's why. And it's part of the NPI of your new product development. It is really a good tool when you are going to market. Why? Because you demonstrate that your line, you understand what you want, what is your failure rate that you want at the beginning, and we can talk about it. But the important part is that you can assess that in a more quantifiable way. Other reasons could be that you decide to test for batch. It could be that you're doing a constant failure analysis as the product progresses. You may want to verify a change in lot, change in design, or a change in production location. That's when you start doing that. So all these things is when you should do it, but at the end of the day, how you should do it is what we're gonna be talking about. Because the how, it will give you the ability to be effective and be able to quantify your risk in the long term. So what it is, just so it's an end-of-line testing, right? ESS kind of end-of-line testing. So people will think about it. So you notice I mentioned failure rate. So imagine you have a failure rate. You understand what that failure rate. And by the way, ESS is just one more of the things people use. Burn-in, HAS, stress screening, all of them use the same methodologies, small variations. In some you have 2 or 3 factors coming to play, but it's almost the same principle. All of them are the same principle. It is a test or it's an evaluation that you want to do of your product at the component or system level right? Let me repeat that at the component or system subsystem level. And then you say, hey, I want to control this certain failure rate, and you have a failure rate over time, like something in this arena. And you decide that you want to control it at that level. There we go. That's the line. And everybody in marketing or in risk analysis says, you know what? That's the perfect level. We want to eliminate that. And you know you produce that, and you know you need to eliminate it because you don't want customers to potentially get that. You want lower failure rates potential in the field. So the question is, what do I need to do, right? That's the one. So that's the most important part. What is that failure rate I want to control? Because that defines what you have. Or you can say, you can do that in different ways, and we're going to cover that in this conversation. So in different terms, we talk about the whys, talk about the what, we talk about the how. So we need to talk now about the how. And the how, how you gonna go about it. So I need to reduce and eliminate that, control that failure rate right there in our previous conversation. But how are you gonna do it? So there are different ways to do it, and quantitative ways or qualitative ways. Qualitative ways, I'm just gonna share this with you. It's not the subject of this conversation, but it could be someone saying, well, I'm looking for 300 degrees temperature. We put it to test. Anything that fails on that, it's no good. We let it pass because we decided that in a room, and we thought that over the years, I have experience. I have 50 years experience, God. And then we decide, by the way, that's good. And that's what you want to control. And that's okay if your organization is willing to do it. The only question with that, someone may ask you, what does that represent in the field? You don't have the answer. Someone may ask you, how does that affect the performance of this component in the field? Well, we never hear the problem, so we don't know, but never hear the problem. So that could be an answer, right? There are answers for everything. So, but that's not the right way to go. The right way to go is you are able to determine, yes, I'm eliminating a certain percentage of the life, and we will cover in that today's presentation. But also at the same time, I know what is the stress level that I want to test, for how many cycles I should do that, and I know I'm catching something. I know I'm eliminating that high failure rate that we see from the beginning. And again, it's usually done when you want to eliminate high failure rates from the beginning. Imagine you have your failure rate inverse, and then you have a low and then increasing over time. You may want to say, hey, okay, uh, that's okay. And then I can do it just to make sure that, hey, I just want to control that I am at that failure rate. Again, right? You do the test, you determine the curve, you say I have a low failure rate, I just want to maintain that failure rate. That could be a methodology. Usually it's expensive, it costs, but for example, in medical industry or pharmaceutical industry, may be important because you want to make sure that you have an evidence that you did not produce something that is questionable. So with that said, let's talk about reliability testing. Reliability demonstration start by understanding how the product is used in the field. You can use standards. Standards don't tell you about reliability. They were decided by committees. Committees sit down in a room and say, well, based on our experience, X, Y, Z, tested to this, and that should be okay. There is more that goes on that committee generation, but in general, usually is between people that perform some kind of job in the area, understand the area, and given the experience, they are suggesting that. It's a good method, but it's not the method. Another one is you now understand your failure mechanisms, you understand how it's used in the field, and now you establish the reliability to that. And reliability is no more, no less than the probability. It's a probability number to performance over time that you will have to a given failure mechanism. What a probability that I will have a failure due to that failure mechanism. So that's extremely important. And from that, you can use thermal chambers, right? You can control that. You can do it by control the thermal mass with chillers or not. You do check on vibration. You can combine with corrosion. You do a failure analysis. You establish from those tests life stress relationships at every stress level or combination of stress levels. And then from there, you establish a probability of occurrence that helps you to understand. That's in summary. That's in general what is called a reliability uh, testing. So in reality, you have two elements, right? We talk about it, qualitative and quantitative, right? So you have both of them in what it means. Qualitative, again, is based on public knowledge. Hey, I think it is. Oh, we do a test. We always did a test at 200 degrees C or at this G for this sweep of frequencies. And if nothing happens, it will be good. You can take that avenue. But is that the avenue? So quantitative offers you a more solid ground. It's a rock solid ESS program based on quantitative. So we're gonna go over how you get to that quantitative part. So there are two types of, when you look about reliability or talk about reliability, there are two types of studies that are done. One is based on what is called usage rate acceleration. So imagine you have a dryer or a washer, and every cycle, the person used the wash 10 times in a week. So 10 hours a week. And then that means it's X amount of hours a month, a week, and possible. You can say, okay, if I keep cycling that, it will get to my life. So I just look at a given life. Okay, I need to assure that at least can do that, right? That could be one way. The only problem with that is the there is a the issue here is that many products have a lot of products at system level, which is usually what is the methodology used for. It guarantees it's difficult to say, hey, what is my lower life? So in this case, what you want to do is what is my minimum life? I'm gonna use, operates of this. I know that historically during the reliability testing and validation of the different systems, you have failures on that occurrence. You have that combined failure history. So now you say, okay, I know I have these failures at the beginning, and I know that after a certain number, it should be okay based on the test that we did. So you go ahead and you say, okay, I leave this unit operating for X amount of time. You can let it go like that. Another technique could be that, hey, it's what is called an ongoing reliability testing, right? A lot of companies do it, industries do also. And mainly what it is, hey, I take samples, I put it on test, and I leave it there. And they keep going, they keep accumulating life as they go through all these cycles. The only criteria here is that you need to make sure that those cycles are representative of the operation. So maybe I'll give you an example. Let me go back to that washer. If you keep running that washer constantly, what are you missing? Well, someone may argue you are missing that the and shut start and shut down for a period of time. So you need to replicate that event. If you run that constantly, you may get a failure mechanism that is not representative of the actual cycling test because that unit cycles on time. So those are the things that you need to pay attention to. So what else? Okay, so another methodology is what is called stress-based, which is the one we're going to concentrate strongly on this presentation. And then what I have here is I have over time, you can see as my stress degrade, my strength degrades, and then it start going down. It start moving below. So that my top level, the green one is my stress, my strength of the unit start weaken. So when that start weaken, my probability of occurrence, my stress versus my strength, start getting under the area. You notice that. And when you go, automatically generates for you a probability of failure. So the longer I use a product, the more propense is to fail because successful failure, degradation, right? It's about life. The longer you go in life, what is the probability? The probability of you having to die at 20 years old is totally different at maybe my age, right? I have a higher probability of dying than a person that is at 30. So hope not. No, in this presentation, by the way, but mainly what it is what we're looking for here. So how that degrades over time. So the objective of increasing stress on ALT is mainly what I'm going to show you here. I'm increasing that stress over stress, right? Instead of reducing my strength, I'm increasing the stress. If you notice in here, I'm doing the opposite, but it has the same effect. And that is the concept of the ALT. What it does is, hey, I'm increasing my stress, and with that, I'm driving the degradation. And why this works? The reason this works is because I'm maintaining the same failure mechanism every single time that I increase the stress. The moment that failure mechanism change, that means that stops. You should not increase your stress more at that point. So one nugget that you need to take with you here is you can increase your stresses, but the moment your stresses that changes your failure mechanism, that means you stop. That is no longer that life that you're looking at. So how you go about it? So we talk about it, and let's go a little deeper. I need to understand my environmental loading. And with my environmental loading now, I understand not only the environmental that I apply, but my operational loads. So I look at my customers, how they use it, and all that. And based on that, I develop what is called now my reliability calculations, and I'm trying to determine based on a physics of failure mentality. It is corrosion, it is fatigue, it is thermal fatigue, or is mechanical type of fatigue, right? They have different variations. It is creep, fatigue, what percentage is. Those are the things. And then based on that, I customize, I allow them now to drag that degradation over time so I can calculate it properly. It's more or less like a DOE. You have a DOE, and then you are controlling those factors, and you are testing to those factors, and you are making sure that you are determining, hey, if that factor is relevant, that is a failure mechanism I want to deal with. So at the end of the day, you will come with a solution that would be something like life stress relationship, where I have for my factors, all my stress levels, right? Temperature, humidity, by G forces, you name it. Could be so many things, voltage, right? Oh, that is now I'm determining, okay, how I increase, the higher I go to the right, the lower is my life. So that is where you go. And then you can determine the probabilities of occurrence. And why this is important? Because this is the basics now that is going to help you to design your ESS. Once you establish this function based on your reliability testing at the different stress levels, you can use the same information now, right? It's about knowledge management. You can use the same information now to design your ESS. So imagine I am at the end of my test. I did a test with 20 samples, and 40 samples at different stress levels in temperature, for example. I get these responses here. Now I can calculate what will be my life to the right. You can see that perfectly. Oh, that usually goes from the left to the right, right? I did it, there's a higher stress, and now I can determine what will be the projection, what will be the life of the product. The other way around now, you use the same information and you come from the left to the right, and you say, okay, what stress level I can go higher? Do I maintain my same failure mechanism? And now I can use that to determine a shorter life. Each one of these will have a failure rate, a curve that it will be increasing failure rate as you go to the left. So if I decide that I have one more stress level that I want to explore to use it for ESS or any other type of burn-in, kind of, I just move, do the test, evaluate it, and now generate that function, and then you can use it. So that is the principle of a metric ESS. So you have an end of the line testing. You will have you're gonna do it for all your products, and you're gonna say, okay, I want to do that. I want to design a ESS. So first, what is my failure rate? Then I determine that. You can see the line there, the red one. I determine that's what I want to get. Okay, so that is my target failure rate that I want to demonstrate. And where is that failure rate? That's your actual use failure rate in the field, because that's the failure rate associated with your warranties, right? You want to make sure that you don't have a higher failure of occurrence from that point to the left. So then you go back to your testing that you did in reliability, right? And now you know that you have that use function. You know you did a high stress level 2, you did a high level stress number 1, and then you determine your use level. You know that the function that we have down in lower is the user level failure rate, and you know that relates to that specific user level. Okay, what is that point? That point is a X amount of cycles or hours. So you get that number of amount of cycles, you place it on the use level function, you establish a line, and now you can go back in any stress level and will tell you how many cycles you need to test for that given stress cycle. So if I want to use I want to do an ESS in this case, and I want to do this stress level 1, it will be, let's assume 1,500 cycles, hours, sorry, hours. And then if I want to use stress level 2, I know it will be 200 hours of test. So now I know that if I want to use high stress level 1, it will be 1,500 hours. If it's high stress level 2, it will be 100 hours. So now you can see how you can establish that. You can see right there how you select the right stress level. You are maintaining the failure mechanisms. You are testing to the highest stress level possible. Or you can say, you know what? We want to do it faster. So you explore a third one here. And then you find out what is that value here. Maybe it's 10 hours, 5 hours, it's 24 hours. And then you go back and execute it based on that. No, those stress levels could be simple stress level, or it could be a combined stress level. Could be temperature only, could be combined humidity with temperature, doubt, because complicated activities with the chambers, or usually it's temperature and vibration. Those usually are the two ones. Now, it could be so many things. And you will see an example I'm going to give you about adhesion. I choose specifically that to show you that it could be anything that you want to use and control in your manufacturing floor. So here is the adhesion example. The adhesion example is more or less now I have my test here from my test that I did. Those are my functions. These are test points, and you can see them. And you notice that you see the blue line to the right. It's what I'm pointed out here to you. That's my my user level, right? Calculated. But this was the stress level 1 is the red one. Sorry, where is my cursor? Yeah, there we go. My cursor here. So this is the stress level 1. This is less stress level 2 is the purple, and stress level 3 is the bluish to the left. You notice the red one, right? You can see there, right there, those points. It's kind of off. There is one off. So we have an early failure and then the other ones. So we have what is called what? Infant mortality failure, right? That's what you want to eliminate. That's what people call infant mortality failure. Those exactly are the ones that you want to eliminate in this case. And then you have, in this one, a high stress level. You say, well, they look almost the same. No, they are not. They are a little different, right? And then you see how different they are because they are early failures or infant mortality failures. And you can see when you look at that same group of data, take a look what happened, how different it is. And by the way, this is just takes you to, believe it or not, it's just a step more that you need to look at those and identify exactly what is the point. And I'm here is telling me, at that stress level, it takes me 100 cycles or maybe 150 cycles, let's assume, right there in the middle, for me to deal with that. By doing that, now I'm eliminating. I know that at that stress level, 150 cycles, whatever fails there will be infant mortality. Whatever pass, it's great. I can let it go. So I can do that at that stress level. And then what is the penalty I pay? Well, that's a reduction in life. I can calculate that. And I will be teaching those during the STAC how to do this analysis, and also I will be teaching also how calculating the remaining life. Well, that's a subject for a different conversation. But you can see here, I'm able to identify those. Once I identify those, take a look. That's the failure rate. Remember that beautiful failure rate that we have? That's a school class. That's typical. That's in general. But you can have a failure rate like this, which is that you have the infant mortality. Once they move out, is a normal failure rate. So I can come back and say, okay, now if I calculate it this way, I can design my ESS to catch any degradation due to adhesion associated with that. In adhesion of what? In this case, I have a surface, I'm putting adhesive, I put another one together, and to block water ingress. Simple like that. So now I know that in 60 cycles at that stress level, I can be catching that in 60 plus cycles. I can say, okay, let's go over the 100 cycles where I start moving to the right, figure it out what is the right level, and then you design it, optimize it for that level. Now you have. That is the advantage of this methodology, because now you are quantifying your real risk, identifying what is the stress level that you need to be using for a given failure mechanism that you want to control and you want to eliminate out of your production, right? Number three, after that, you can calculate the remaining life of your product because you need to know, hey, how much is the remaining life of that? And third, now you know that the products that pass that test will not have that. It will show the normal degradation. So that in conclusion, so we can open the floor for any questions. Yes, is this ESS program, which is reliability based, you determine for each stress your failure rate. You can combine, as a note, you can combine your failure rate with those systems. So now you can combine and you can have two factors. The important part of that is looking at the interaction of the two factors. And this is very important. If you have two factors, imagine temperature and humidity or temperature and vibration. And you can say, hey, are those factors working in my favor or against me? You need to do a DOE. A DOE can tell you, hey, those two factors are affecting me at the same time because of the interaction between them. Yeah. So in those cases, it makes sense for you to use both. But it could be that both of them are independent. They don't affect each other. They don't have interaction. There's no interaction, very low, none. So in those cases, you will be very simple by breaking the test into two parameters. Or maybe one of those is the most critical that drive really your failure mechanism. Those are the things that you need to look into. The stress level is selected, right? Once you select the stress level, right? I have a target. I determine that's my use level. I have my stress levels that I want to use, right? And my use level. Now I go about, okay, what is the right level I want? And then I drive for that. And now I determine with whatever stress level I want. Now I can determine the number of cycles, hours that I need to do in environmental stress. The most important, there are two important things. One, that you are addressing the failure mechanism, right? Because if any one of these scores has a different failure mechanism, that's where everything goes wrong. So you need to make sure failure mechanisms are the same. Second, that you are designing the test and that your remaining life, the remaining life of that product or that component is at the right level that your customers are expecting. And the third, you need to make sure that all this you build the knowledge over time. So the organization understand why it was selected, why is designed like that. And you need to also understand in that process what are the elements of that design that if changed will make you to go back and take a look at these curves and making sure that they are correct or they are not affected. So with that say, I want to say thank you for the opportunity of speaking to you and in your lunchtime or after 1 p.m. if you're in the East Coast. And also I want to remind you that I will be teaching design for reliability concepts during the ESTEC. I will be teaching reliability data analysis. And if you remember how to break down that curves, remember that I was able to break it into two variables and combine them and show them, hey, these are infant mortality and this is normal behavior. And that will help you to better design ESS. Physics for failure teach you about the concept of that. And based on those elements now, drive how to design accelerated life testing and ESS design, proper ESS design.